Hey, it's Mr. Lum, and we're going to be learning a little bit more about radiation and half-life. So before we talk about what half-life is, please remember that we studied already alpha, beta, and gamma decay. Now, the big question is that type of decay happens all by itself, but when does it happen? And that is going to depend on what chemical is or what element is decaying and what kind of decay it is. So radioactive decay happens because an isotope is unstable. So decay happens anytime. It's somewhat unpredictable. We don't know when a particle is going to decay. However, we can use some math to try to figure out what percentage of particles are going to decay over a certain amount of time. We call that probability. So probability is a measure of how likely an event is about to happen. And for half-life, half-life is the time it takes for half of a radioactive sample to decay. And so we can just estimate roughly, given a certain amount of particles, how much of it's going to decay and how much time it's going to take. So let's take a look at it like number-wise. So what I mean by half-life, if there's no time has passed, you have 100% of the parent and nothing has decayed, so therefore you have 0% of the daughter. After one half-life, half of the parent has decayed. So now you're at 50%. After two half-lives, you're down to 25%, half of the previous amount. And then after three half-lives, we go half of the previous amount again. So half of 25 is 12.5. After four half-lives, again, it's half of the previous amount. So half is 6, and then 0.5 is 2.5. So 6.25. Okay, now what about the daughter? Okay, so we started off with 0, and after one half-life, half of the parent turned into daughter. So the other half is located being daughter. Now, if these two numbers add up to 100%, these two numbers must add up to 100. Okay, so again, if here's the number 50, half of it decayed, and we're now at 25. Okay, then where did that 25 go? It turned into daughter. So that 25 gets added to this 50, so 75. Again, 12.5 is going to get added to the 75. So that's going to be 87.5. And then 6.25 is going to add to that 87. So that's going to be 93.75. Okay? At all these points, all these numbers always add up to 100%, or the total amount that we started with. Now, this is based on mathematics. So if you went for 5 half-lives, it'd be 3.125, okay? And the numbers would just keep getting smaller and smaller and smaller, okay? But what you would find is that mathematically, those numbers would never reach 0. They would never reach 0, okay? Because it's based on math. Now, in real life, it will reach 0 eventually, okay? And that's where kind of the math problem kind of breaks down. So here we see the same thing. Here's the parent. We start off with 100%, and then we go down to 50%, 25, 12.5, 6.25, and then it would go 3.125. And what you can see is that it'll never reach 0, but after many, 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 many half-lives, it will eventually all turn into daughter material. So let's do a little practice question right here. So if we are told the half-life, we can use it to calculate the mass before and after a period of sample. So here's our example. The half-life of zinc happens to be 2.4 minutes. If you begin with a 50-gram sample, what mass will remain after 9.6 minutes? So in all half-life questions, I like to make a table. So I like to write the half-life, maybe the time, and maybe the parent, and maybe the daughter. Sometimes I don't write all of these little things in there, but for this first example, I'm going to write everything. So we always start off with 0 half-lives is 0 time. It says that we start with a 50-gram sample, so we're going to write 50 for the parent. And that means we have 0 daughter. After 1 half-life, which takes 2.4 minutes, we have half the amount of the parent, so 25. Okay, the other 25 turn into daughter. After 2 half-lives, the amount of time that has passed is another 2.4 minutes. So add 2.4 to this 2.4, and we'll get 4.8 minutes. Half of 25 again is 12.5. Okay, so I now add 12.5 here. It's going to be 37.5. For our third half-life, we're going to add another 2.4 minutes. So carry the 1. And then this is going to go down again to half. And then this one is going to increase by that. After 4 half-lives, we're going to add another 2.4 minutes. And then this is going to go down by half again. And then this one's going to go up by that much. So, but the important thing that we also notice here is that we reached our target number, 9.6. So the question says, what mass will remain after 9.6 minutes? We just read it off the table. The amount after 9.6 minutes would be 3.125 grams. And that's our answer. So you can also graph this kind of stuff. Now, this is just like the table that we had before, except that we start with 100%. After 1 half-life, we're down to 50. 2 half-lives, 25. 3 half-lives, 12.5. 4 half-lives, 6.25. And you see that this decay curve will never technically reach 0. In real life, it will be 0. There will be a point when all of it has decayed. But mathematically, this is where it kind of breaks down a little bit. So, same thing. Here's another decay curve. But say if we started with 10 grams. After 1 half-life, it's 5 grams. 2 half-lives, half of that, 2.5, 1.25. Now, each half-life is different. In the previous question, we saw a half-life of 2.4 minutes or something. For this strontium half-life, 1 half-life is 29 years. So if you start off with 10 grams, 29 years later, you'll have 5 grams. Another 29 years later, you'll have 2.5 grams. Now, there's a lot of different common half-lives. First off, there's a lot of different half-lives. Hundreds and hundreds of different elements will have half-lives. These are the most common ones. And probably the first three is what we're mainly going to be using. Okay, so the half-life of carbon-14 is 5,730 years. The half-life of potassium-40 is 1.3 billion years. And this is, so the next big question is like, what's the point? Like, what can you do with this information? Well, what you can do with it is something called carbon dating. And so radiocarbon dating is when you're using a ratio of the amounts of carbon-14 and carbon-12 in a dead organism to find the date when it died. So you can figure out by looking at some old bones or like a very, very old tree that has died a long time ago and figure out when exactly did it die. Now, when an organism is alive, it consumes a bunch of carbon-14. It consumes that carbon-14 in food it eats. Like if you eat some fish, you'll have carbon-14. And you will start to release a little bit of radiation from eating that carbon-14. Now, we can't do any carbon dating on you right now because you're constantly eating more food and constantly replenishing the carbon-14 that you have lost. But there will be a point in every living thing's life when it dies. And that's when it stops taking in more carbon-14. And that's when the amount of carbon-14 that it does have then starts to decay. And we can use that information to figure out how old those fossil or those bones were, right? So we can look at all that kind of stuff and figure out when did organisms die. For example, when we look at when first peoples, indigenous peoples came to North America, they crossed the Bering Land Bridge. And how do we know this? Well, we can find remains from 20,000 years ago and figure out when that was 20,000 years ago because of carbon-14. So when you see things like, oh, these people lived here, 25,000 years ago, or the Egyptians were here, 5,000-6,000 years ago. All of that information is obtained by using carbon dating. We can figure out how old it is. We don't have to put it to just people either. Like when we want to know when was this particular mammoth alive, well, we can do some carbon dating and figure out this mammoth that we found an old tusk of or whatever was here 50,000 years ago or whatever it was because of carbon dating. So we're going to do a little bit of practice questions right now, and then you're going to get some practice on this stuff. So here's a decay curve. And the first question is, what is the half-life of uranium-235? So if we want to find the half-life, we start with, here's 100%. What is the half-life of this thing? Here's where it's 50%. Go across, we find it right there, then we go down right here. Okay, so that is the 50% marker. I'd probably say it's more like right there. But if this is 1, 2, 3, 4, 5, so every one of these numbers represents 200. So that's 400, 600, and then it's 800 right here. I would say it's just shy of 800, so we'll say 750. Now we make sure to read it. It's not just 750, it's 750 million. So that is the half-life of uranium-235. Now, it says, what percentage of uranium-235 remains after 1420 million years? So we can, sorry, that's going to be roughly, so here's 1,000, 12, 4, right about there-ish, but I can see that this is roughly double our number that we thought right here. So it's going to be roughly 2 half-lives. There's going to be roughly about 25-ish%. Okay. Now on a test, if I said that it was 750 million years and you said it was 700 million years, I'd still mark you right. You're still within that range of being correct. And if you thought, if I say this is 25% and you thought that it was 22% or 20%, you're in the range of being correct. Now, the next question says, the daughter product in this decay is lead-207. What percentage of the total possible amount of lead-207 has been produced after 1,420 million years? So, if we have 25% that's left over, that means 75% of the total amount has been is now lead. These two numbers still have to add up to the total. Now, before we get into these next questions, I want to emphasize a few things. These half-lives and the concept of half-life is a mathematical thing. It kind of breaks down a little bit, and mathematically, the half-life will never reach 0. However, in real life, it will reach 0. So when you're doing carbon dating, the half-life for carbon is 5,730 years. But the effective range of using carbon dating, it can't figure out how old something is if it's more than 50,000 years old. So carbon dating is really good for figuring out things about human beings, Ice Age kind of stuff, things like that. It's not good for figuring out when did that particular dinosaur live and die, because carbon dating is only really good at figuring out how things that are up to 50,000 years old. So what would we typically use for, say, figuring out how old a dinosaur was? Well, dinosaurs were 70-ish, 65, 70 million years ago. So uranium-235 half-life is 710 million. And the effective dating range is somewhere greater than 10 million years. So could we use uranium dating to figure out how old a dinosaur is? Well, the problem with uranium dating is that dinosaurs typically didn't have a lot of uranium in them, so we wouldn't use uranium dating. However, we would use potassium dating. Now, potassium has a half-life of 1.3 billion years. But the effective dating range we could use potassium dating is for things that are greater than 10,000 years old and up to 3 billion years old. Okay? The Earth is only 4.5 billion years old. So potassium dating is really useful for that kind of stuff. Now, which parent isotope has the slowest rate of decay in the above? Well, even though 5,730 years is really fast, really a long time, sorry, it's very, very fast compared to these other ones. So the longest one is potassium. Okay, So potassium 40. Now, state which isotope would be used for dating the material that is 3,000 years old. Well, carbon. What about 30,000 years old? I'd still use carbon. But if you wanted, you could use potassium. What about 60,000 years old? Carbon its limitations have been reached at 60,000. Probably want to use potassium. What about 60 million years old? Still use potassium. We've surpassed the effective dating range for carbon, but we could use uranium. And sometimes we use that kind of stuff to figure out how old certain types of geological structures are. Like certain mountains or rocks or whatnot. If an original 10-gram sample of carbon-14 decayed for 11,460 years, what mass of the nitrogen-14 would have been produced? So carbon-14 will turn into nitrogen-14. So it's asking me a years and all that kind of stuff question. So what I usually do for when I get like these kinds of half-life questions is, like I said, I make that table. Now, here's my half-life, my time, and my parent. Sometimes I put the daughter on here, and sometimes I don't. It depends if it asks for it. But this one's not asking for it, so I'm not going to bother writing the daughter. You always start with 0 half-life and 0 time. And then it says we start with a 10-gram sample. After 1 half-life, the half-life of carbon-14 is 5,730 years. That'll decay down to half of it, 5 grams left. After 2 half-lives, it'll be another one of these things. $11,460 years. And we'll have 2.5 grams left. Now this 11,460 years happens to be our target number. And so what mass of nitrogen-14 would have been produced? So it did ask for the daughter this time, and I didn't write it. So 0. Where did that 5 grams go? Went to daughter. Where did that 2.5 grams go? It also went to daughter. So our mass of nitrogen-14 is 7.5 grams. The next question says, which of the 3 parent isotopes decays through beta decay? So beta decay is going to be changing, like for example, carbon-14, which is 6, 0, -1, that's beta. This is a beta particle. And so that's going to turn into carbon is beta decay. This is beta decay right here. Okay? A real key thing for helping you figure out which one is beta decay and which one is not beta decay is look at that mass number. Are those mass numbers the same? And for carbon, we see that the mass numbers are the same. They're both 14. Now, let's take a look at potassium. Potassium is turning into argon. Okay? Now, you probably were thinking like, hey, they both have that 40 there. That one's also beta decay. Let's write this one out. So we write potassium, 40 and 19. And then we're going to turn this thing into argon. Okay? And argon is 40 and 18. So, do I put a -1 here? That won't make it equal. It'll actually be a 1 right there. Okay? And this is something a little bit different. It's called a type of decay that we haven't really done a lot of. It's called like proton capture. But this is not beta decay. The only one that's beta decay is this one. The math doesn't add up. If I try to put beta decay in here, it'd be 0, -1. 18 minus 1 doesn't equal 19. So that is not beta decay. Only this one is beta decay.